Today I introduce the material and the process to make the material about the photocatalytic titanium dioxide material for environmental purification. So photocatalysis is this very simple subject. Only two keywords: titanium dioxide and light. If titanium dioxide material irradiated by light, then go to the air cleaning. All of the organic compound decomposed by this photocatalytic reaction. Then go to the water cleaning. Even the bacteria and weeds also killed by this photocatalysis. So important subject is self-cleaning property. So one is the decomposition of the oil dust, and this photocatalytic material shows the super hydrophilicity. So if photocatalytic coating material, then light irradiating, next day raining. So some dust on the photocatalytic material automatically removed by this self-cleaning property. Then now this technology applied to the many industry, not only Japan but also worldwide, Korea and Lithuania and European country. So this building also is in front of a Tokyo station. This building is coated by photocatalysis. Then on this home house, this is rapid train in Japan named Shinkansen. Nowadays in Shinkansen, we cannot smoke a tobacco, but a special room set at this photocatalytic air cleaner to remove the smell of a tobacco. Then go to another application also is applied in the industry. So Professor Akira Fujishima and our director, he discovered water splitting by titanium dioxide more than 50 years ago. So titanium dioxide material immersed in the water, then solar light irradiate. Only sunlight decomposes water to hydrogen and oxygen. This is a dream technology to get the hydrogen energy, only water and sunlight. Then he published in Nature paper 1972. So this is a citation number at each year. This yellow curve is this Nature paper from Professor Fujishima. Nowadays, this total citation number is more than 12,000. So monster paper. Then this green curve, Professor Tama he belongs to the Toyota Mobile Company's Institute Research Center. Then he announced in Science nitrogen doped titanium dioxide. If titanium dioxide doped with nitrogen, then active to the visible light. Generally, titanium dioxide, pure titanium dioxide, only active to UV light because match to the semiconductor band gap. So this black line, black titanium dioxide, Dr. Chen from UC Berkeley, so he announced in Science 9 years ago, this is very unique material, black titanium dioxide. So this white color, this is pure titanium dioxide, shows a white material. After this treatment, this white powder changed to black. So they named this is black titanium dioxide, black TiO2. But in this case, high pressure hydrogen at high temperature, 200 degrees, and it takes long time, 5 days. Then this white material changed to black one. Then they check the XRD spectra. Before and after this treatment, XRD spectra is not changed. That means only subsurface is changed, oxygen vacancy. Then color is changed. Bulk materials keep the anatase, same structure. So, according to the photocatalytic reaction explained by the Gibbs free energy, so one is an uphill electron transfer light irradiated to decompose water to hydrogen and oxygen. In this reaction, gives free energy is positive. So we call this reaction artificial photosynthesis. Then this is downhill electron transfer reaction. Gives free energy is negative. In this case, organic compound is oxygen from the atmosphere. Then under the photocatalytic reaction, this organic chemical decomposed to carbon dioxide and water. So this reaction applied to the environmental purification. Today I report about this downhill reaction. So this is a schematic image how to work a photocatalysis. This is titanium dioxide material. Then light more than band gap energy irradiated to this semiconductor material. Then excited electron and hole is produced. Then these electron carrier should be suppressed by this recombination. Then this carrier go to the surface of the material to react with water to go the hydrogen or some chemical decomposed to the carbon dioxide. So important thing is to keep this valence band position. This is the originality of titanium dioxide because this valence band position so strong oxidation power. So to enhance this photocatalytic activity, in this paper announced heterojunction and crystal phase heterojunction created space charge accumulation, depression at the interface and promote the separation of photo-generated electron hole pairs. So in case of titanium dioxide, we know the three major crystal phases. One is anatase, rutile, and urkite. This anatase and rutile and this combination, AR heterojunction, is a common material and already commercialized this material. But this urkite this is rare material and difficult to make this urkite structure of titanium dioxide. Then this combination, AB heterojunction and BR heterojunction, also difficult to make this material because generally starting materials anatase transit to another crystal phase. In that case, the conventional route is a high temperature treatment around 700 degrees. But problem is sintering at a high temperature. Nanomaterial of titanium dioxide sintering at high temperature. So our strategy is partial heating in cold condition to make this another crystal phase, urkite and heterojunction materials. So today I report about a new process, a very unique process to make this material, and second one is how to work this new material to active the photocatalytic reaction. So this plasma in gaseous phase, this is well known and already utilized semiconductor manufacture to make the thin film using the sputtering and CVD. In case of a solid phase plasma, this also is named plasma phenomenon. But how about plasma in liquid? This is very new generation plasma technology, undeveloped field. Today I introduce in liquid plasma treatment of titanium dioxide. This is the actual movie in liquid plasma. Plasma produced in liquid. This is very difficult to this plasma. How to make this plasma in liquid? You are between two electrodes applied high pulse power voltage. Then Joule heating and bubble coming between two electrodes. Then inside the bubble, avalanche breakdown and plasma produced in this liquid. So this plasma is located by the gaseous phase, and this gaseous phase is located by the solution in liquid. In our case, it's water. So this plasma is located in water. That means the temperature is so low, less than 100 degrees. Then active radical and species is coming, so many active species coming to this plasma. So this is a schematic image of how to make titanium dioxide treatment using in this liquid plasma. This titanium dioxide nanomaterial, this is commercial products from Ishihara Sangyo company in Japan named ST01. This is already applied to many application fields, photocatalytic coating. So this starting in materials, nano size, another structure. Then after treatment, this pure pristine TiO2 white powder change to these colors after this in-liquid plasma processing. So this is without treatment of starting material, and after plasma treatment, this SEM image almost same. That means keeping the nano size. If this pristine TiO2 treated high temperature under the hydrogen streams, that case, nanomaterial sintering and crystallines are bigger size. So our strategy is keeping the nano size and to change the phase transition starting material. So this is check the X-ray spectra, and after cellular treatment, all of the no change of the starting another crystal. Then this is the STEMIO image of pristine TiO2. So we check the 100 and 101 another phase. This is starting material. Then this is after plasma treatment. So partially volcanic structure is coming among this another structure. So we make heterocrystalline phase of another volcanic under this plasma treatment. And more surprisingly, subsurface of nanomaterial changed to this one. See amorphous disordered shell around the titanium dioxide materials produced after plasma treatment. So maybe this disordered amorphous phase is the origin of the color change. This diffuse refractance spectra, this spectra means light adsorption of the material. So this curve A is pristine TiO2. So visible region is no adsorption. But after plasma treatment, this orange line is visible activity. But this band edge position is same without plasma treatment. That means band gap position of this titanium dioxide after plasma treatment is almost same. So this dotted line, blue line, is a nitrogen doped titanium dioxide. This case, this band edge position is shifted to visible light. So we call this is visible active photocatalysis, and this also is commercialized. So we study the environmental purification of this photocatalytic reaction using the ISO standardization method. So firstly, on the glass sheet, this photocatalysis material is pure water dropped and dried at 60 degrees, replaced by air with 50% humidity. Then UV light irradiate for almost 1 day to remove some chemicals, impurity. Then go to the main experiment. Again, replaced by air with 50% humidity. Then go to the acetaldehyde. This model compound of organic chemical. Introduce this chamber. Then keeping the adsorption equivalent. Under this condition, we monitor the acetaldehyde and carbon dioxide concentration by gas chromatography. So this is result. So this is a equation of acetaldehyde decomposed to carbon dioxide. Please see this molecule weight 1/2. So this region in the dark area, just acetaldehyde adsorbs on this material. So at this point, light irradiated. In this case, we used fluorescent lamp like this one. Then this acetaldehyde concentration go to 0 immediately. That means photocatalytic decomposition is produced on this reaction. Then, important things about this carbon dioxide. So this white sac is pristine TiO2. Carbon dioxide around 100 ppm, almost same acetaldehyde. But after plasma treatment, this material shows twice of carbon dioxide. That means 1/2 completely decompose this acetaldehyde using this plasma treated sample. So this green line is a nitrogen dot visually active photocatalyst. So our material shows a highly active photocatalyst under fluorescent lamp. So we studied why our sample shows this visual activity using fluorescent lamp. This is action spectrum. So x-axis is irradiated light wavelengths, and y-axis is quantum efficiency from the acetaldehyde to carbon dioxide. So this black line is pristine TiO2 and red line as after plasma treatment. Please see around here, visual region. Both samples shows no activity at around 420 nanometer wavelengths. But our sample, this activity is more than 2 times higher than pristine TiO2. That means our sample doesn't show the visual activity, only enhance the UV region quantum efficiency. So we checked ESR spectra. This black line is no treatment and red line is a plasma treated sample. So we get the O2 minus signal. This O2 minus means the oxygen vacancy of our sample. Oxygen molecule come to oxygen vacancy, then couple to the electron. Then our sample shows the O2 minus signal under this ESR spectrum. So we consider why our sample shows this UV region activity. One is oxygen vacancy near the sample. Oxygen vacancy traps the oxygen molecule from the atmosphere. Then light is irradiated. Excited electron coupled this with oxygen molecule to produce the active oxygen species. This is the active oxygen species decomposer of chemical. Then second thing is a combination suppression model. So our sample has oxygen vacancy. This oxygen vacancy has a subsurface of this band position. Then excited electron is trapped to this oxygen vacancy side. Then this electron and hole is suppressed on this oxygen vacancy sample. So we study the stability of our material a long time, almost half year. This activity is keeping. Then now we improved to get a high amount of treatment sample. So this is batch scale is bigger size plasma treatment. Now is a flow system. This flow is around 7 liters per minute, including nanomaterial. High flow rate and high volume material treated in this system. So this is my conclusion. Is one is in liquid plasma processing produced a highly photocatalytic active TiO2 nanomaterial. In case of acetaldehyde experiment, the treated TiO2 shows the fast decomposition to carbon dioxide under fluorescence. From the action spectra, the treated sample enhanced at only UV region. Finally, origin of high activity attributed in the oxygen vacancy near the nano-sized TiO2 material, as well as the heterojunction, anatase and fluoride. So this is acknowledgement to budget and main experiment completion by these students. Thank you for your time.